This video covers the substitution method, which was one way for solving linear systems when they had one solution. The main idea is to solve one equation for one of the variables, and then we're going to substitute it into the other. When we perform the substitution step, we get left with an equation in a single variable, and then we solve that equation and back substitute. So the 5 steps are to isolate one variable using one equation, substitute into the other equation, solve our new one variable equation, then back substitute, so take the solution for the one coordinate and use it to find the other in either equations. And remember, we should always check, which we can do by verifying that the point is a solution to both equations. We also can do it by graphing the equation and identifying that the point of intersection is the point with the coordinates we have found. So I'm going to start with a really basic example where it almost doesn't feel like what we're doing is substitution. Equation 1 here will be the equation x equals 12y minus 4, and the second equation will be x equals 9y plus 7. Now in this equation, I noticed that in both equations, x is isolated. We should confirm for ourselves that we know that this equation does in fact have a solution. These two equations do correspond to lines with different slopes. Typically what I want to do is isolate one of the variables. So I look at the two equations, and what I want to find is in one of the equations, hopefully I see one of the variables showing up by itself. That's step 1, deciding what that isolation is. So deciding I'm going to use that as my candidate to get going. In the second example, we'll see how you might have to do this by a series of steps. So you might have to do algebra first in that isolate, but in this case, we do not have to. Now we're going to look at the other equation. So my other equation here was the equation x equals 9y plus 7. I'm going to take my expression for x that I found in the first equation, and I'm going to substitute it in for x. So I'm going to write the new equation, 12y minus 4 equals 9y plus 7. That's the substitution step. Now that I've done my substitution step, I have an equation in one variable. So in step 3, I'm going to go ahead and solve that equation. So in this case, I want all the terms with y in them to be on the same side. I'm going to choose to subtract 9y from both sides. That's going to give me 12y minus 9y minus 4 on the left, and 9y minus 9y plus 7 on the right. Those 9y's cancel with one another. On the left, I'm left with 3y minus 4 equals 7. Now, in order to make it so that the y terms are all on one side and the constants are on the other, I'm going to add 4 to both sides. That eliminates the 4. I'm left with 3y equals 11. So y is 11 thirds, just by dividing by 3. So now I know one of the two coordinates of my point. In step 4, I'm going to do what we call a back substitute. It gets its name because I substituted in order to find y, but now that I know what y is, I'm going to stuff that back in one of my equations, or in order to find the second variable. And if you replace it with that isolated expression you found in step 1, this becomes really efficient. So I'm going to take my y equals 11 thirds, and I'm going to go back and look from step 1 at the equation I had that tells me how to find x if I know y. And I'm going to substitute in so that x equals 12 times the 11 thirds I found from y minus 4. And what do I get here? I get x equals, I'm going to rewrite this as 3 times 4 times 11 all over 3. So I can cancel the common 3, minus 4, and I get 44 minus 4, or 40. So now that I know that x equals 40, notice that my candidate for my solution is the point with x coordinate 40 and y coordinate 11/3. To confirm that this is in fact the solution, I would then check it in both equations. Notice that we effectively already checked it in the first equation. If we put 11/3 in for y, we know we're getting 40 out. So I really only need to check it in the second equation. The first one we already did. I want to know, does 40 in fact equal 11/3 times 9 plus 7? Well, 11/3 times 9, that's 99 over 3 plus 7. And 99 over 3 plus 7 would be 33. Does 40 equal 33 plus 7? Oh, yes, it does. So we have, in fact, verified this is a solution. And we can see that our answer is correct. Also, if we were to graph the equation, the two equations, we're saying that this system would demonstrate an intersection at the point 40, 11/3. Let's look at this now in the context of a more complicated example. In this example, we're going to solve by substitution for the following system. 2x plus y equals 7, and 3x minus 2y equals negative 7. I want to start out by just looking at the system, and I'm seeking to isolate one of the variables. That is step 1, is to isolate. So when I look at this system, I notice that y shows up right by itself. Therefore, I think it would be fast for me to solve that equation for y in order to have y isolated. I've done the work for that here below. So the first thing I did was subtract 2x from both sides of the equation, and that left me with the equation y equals negative 2x plus 7. So we're going to carry that along with us, and we'll write that right up on the right here in the next step. So we know that y equals negative 2x plus 7. Now the second step is the step that gives this its name. We're going to substitute. We're going to now look at the second equation, and we're going to replace y with our new expression for y that we wrote down from our solution. So the way I've denoted that here is the new way of writing y, and I'm just going to take it and I'm going to replace it in for y. Writing that below, that means I'm not going to write 3x minus 2y equals negative 7. I'm going to write 3x minus 2 times my expression for y equals negative 7. And that's step 2. In step 3, I'm going to take that new equation. So this is the new equation that we got. Notice it's only in one variable. And I'm going to go through the process of solving it for the variable that remains. So in this case, that first step is to distribute the negative 2. I've got negative 2 times my expression for y. So I'm going to multiply negative 2 by negative 2x. And I'm going to multiply negative 2 by 7. Negative 2 times negative 2x, that gives me my 4x term. And negative 2 times a positive 7 gives me a negative 14. Now I have two terms that are both in terms of x, 3x plus 4x, and I've combined them. That gave me my 7x. So I have 7x minus 14 equals minus 7. In order to isolate the x, because I'm solving for x, I now need to get rid of that constant, that's any constant terms that are on the same side of the equation through addition or subtraction. Because I see a negative 14 on the left, I'm going to add 14 to both sides. Adding 14, I get minus 14 plus 14. Those terms cancel. And negative 7 plus 14 on the right, that's a positive 7. So I get that 7x equals 7. Dividing by 7, I find out that x is 1. So once I've isolated and substituted, now I know the one of the two coordinates of the equation, as long as I didn't make a mistake, is 1. Now that I know one coordinate of the equation, let's go find the second one. So in the last step, we found x equals 1. I'm going to substitute x equals 1 into one of the equations. Now, I chose, because remember we had solved equation 1 for y and written it as y equals negative 2x plus 7. I decided, hey, it might be really fast to take that equation and just replace x with the number 1. So x equals 1, I've written 1 here in green to show where I substituted. And that made it really fast for me to find out that y was 5. So our solution that we have, at least we still need to check it, is that x equals 1 and y equals 5. So all I did was replace x with the number I found from the previous step. We call this back substituting, because it's getting put back into the same expression that I isolated for in the first place. Last step is always to make sure we check. Now, as I mentioned before, we actually knew it was going to satisfy this first equation unless I made an algebraic mistake. That's because I replaced the x I knew with the x I had found in order to find the y. So if the x and y didn't work in equation 1 here, that's a sign that I made an arithmetic error right near the end. I'm also checking it though in equation 2. Does 3 times 1 minus 2 times 5 in fact equal negative 7? Yes, it does. That's 3 minus 10. And therefore, I have established that the point 1, 5 would be on the equation of both lines for the system, and therefore would be the point where the two lines intersect. It satisfies both equations. It's my solution. So a final way to write my answer is a sentence like I have highlighted here in pink. Let me show you quickly just what that looks like all together. So now that we've broken down each step and sort of had it on one screen, here they all are together. First, we isolated. We used that to substitute it into the equation we had not isolated with. We solved that equation, getting one of the coordinates. We back substituted to get the second coordinate, and then we checked that it worked, giving us our ordered pair.